afternoon session. So the speaker is Aninda Sinha from the IISc Bangalore. He will talk. He will teach the string bootstrap. Please welcome him.
Okay. Okay, thank you very much. Let me begin by thanking the organizers for organizing this nice school. And this is my first visit to Korea, so although I've been invited several times before, it's the first time I was able to take this up. So the title of my lectures is String Bootstrap. Now, before I begin the lectures, I would like to take an audience poll. So how many of you have done a course in string theory? Okay, how many of you know what the bootstrap is? Okay, a few more. How many of you think string theory is useless? Justin there. Very good. So I'm going to try to convince you otherwise. And the plan of my lectures is that in the first lecture, I'm going to tell you about the historical origins of string theory. This is usually never covered in any standard textbook. And so the reference for this part is going to be a beautiful collection of reviews in the book called The Birth of String Theory. This is edited by Capelli et al. And this is CUP 2012. So from here, I'm going to go to the 4-particle and 5-particle amplitudes. So I believe that this is going to take the major part of the first lecture and maybe a little bit of the second lecture. In the second lecture, I'm going to turn to dispersion relations. How many of you know dispersion relations, have heard of dispersion relations? Okay, so I'll try to give an overview. So the second lecture is going to be fixed T dispersion relations. The third one is going to be a new dispersion relation, which is going to be called the stringy dispersion relation, which is going to give us some nice new formulas for standard string theory amplitudes in the 4-particle case. And depending on how far I reach in the third lecture, I will resort to numerical bootstrap or some tests in the final lecture. So let's begin with 1. So the history of the birth of string theory. Now, contrary to what you might be thinking, or you may have formed the opinion, string theory actually was trying to, the origin of string theory is rooted in trying to explain experiments. In the 1960s, this was pre-QCD, people were really confused about how to understand strong interactions. And they had data, but then they didn't know how to interpret them. So this is trying to understand strong interactions. And so they didn't have the quark picture. There was a period of a phase of time where the founding fathers of quantum field theory were ready to disown quantum field theory in favor of what is called the S-matrix bootstrap program. So instead of quantum field theory, the favored approach, a favored line of attack was S-matrix bootstrap. So this is an old idea. So depending on the phases, the S-matrix was introduced by Wheeler in 1937, then taken up by Heisenberg in 1943. And this is a curious phase of time because he was supposed to be developing the bomb for the Germany, but he seemed to be busy working on the bootstrap. And basically championed by Geoffrey Chew in the 1960s. And the idea was that instead of the field picture, where we never actually directly detect the field, you would work with quantities that could be measured directly. So work directly with observable quantities. And the data at that point of time, which people were struggling to explain, was the following. So there was something which was called the Chu-Froschi plot. There's a C somewhere. Yeah. And the Chu-Froschi plot took the following shape. If you plot the spin of the particle versus the mass square of the particle, people had observed mesons at that point of time, and they found, and I need to get this right, the intercept has to be correct, otherwise I'll get the rest of the story wrong, that they lay on so the particles lay on a trajectory. So this straight line is called a trajectory, and on that lay particles of known masses. This is literally not on the line, around the line. There's some error bars. So for example, the rho meson would be lying on such a trajectory. And with increasing spins, there would be particles that were found. Now, most of these particles had a lifetime, so they were not stable particles. So in a scattering amplitude, you would see them as a broad peak. But many of these trajectories, which were observed for mesons, for baryons, all seem to lie on a straight line. And these were called Regge trajectories. And this series of particles, this whole tower of particles that lay on this, was called a reggeon. Now, on top of these reggeons, which had intercept half, so this half is an useful quantity to remember, there was also another trajectory which had intercept 1, which was called the Pomeron. So just to give you a time scale, the Regge trajectories were, roughly speaking, in around 1959. And the Pomeron was named after Pomeranchuk. So the Pomeran, this is depending on where you want to give credit. It is either 1956 or 1963. So this Pomeron is a trajectory that is used to explain certain high energy features of amplitudes. So as you can see, I've not marked any particles in the Pomeron because it's not really clear what particles lie on the Pomeron trajectory, unlike the Regge trajectories. So in modern language, these Regge trajectories can be reinterpreted as open strings, and the Pomeron can be reinterpreted as closed strings. And the thing to note here is the intercept here is 1, and the intercept here is half. The reason why I'm emphasizing these numbers is because it will turn out that when you do things consistently in string theory, you're not going to get these numbers. You're going to get some others. So just to put some equations here, the equation that you get approximately is that of a straight line. Conventionally, this is denoted by the function alpha. And if you do a Taylor expansion of this function, and it's approximately a straight line, you're going to get a constant, which is the intercept, and a derivative of alpha, which is alpha prime. So those of you who know that in string theory, the tension is called alpha prime. This is the origin of the notation alpha prime, and alpha prime times m square. And phenomenologically, alpha 0 is supposed to be less than 0.5. This is a dimensionless quantity, and alpha prime is roughly 0.9 GeV inverse square. So this was a data that was available at that point of time. And the other thing that was available was due to a famous paper, this was basically the origin of string theory can be attributed to this paper by Dolan, Horn, and Schmidt. So this is 1967. It was published in 1968. And Dolan, Horn, and Schmidt were postdocs with Murray Gell-Mann. And what they were doing was trying to analyze pion nucleon scattering. So they looked at pion nucleon scattering data. And they made a couple of bold statements. Well, if you read the paper, then you will see that they were very reserved in their statements. So the statements were, first of all, that unlike Feynman diagrams, where you add channels, so if you have a scattering amplitude, let's say, typically you have S channel and you have T channel, depending on what kind of particles you are scattering. So let's, for argument's sake, consider colored scalars, then typically you have two channels. If you have identical scalars, there'll be the third channel as well. So this is what you have in QFT. From examining this, they conjectured that the amplitude, so this is the total amplitude. The total amplitude actually has two pieces. There is the imaginary part or the absorptive part of the amplitude and also the real part. The data, in the data analysis, they were looking at the absorptive part, but using that, they concluded that the total amplitude can be expanded either in terms of the S channel poles. Notation is the following. So S is a Mandelstam variable. So depending on your sign conventions, it's either minus P1 plus P2 square, and T is minus P1 minus P3, P2 minus P3 squared. So this is the S channel, and this is the T channel. So either you expand in terms of the S channel poles or you expand in terms of the T channel poles. And so this is very different from Feynman diagrams, or at least this proposal is very different from Feynman diagrams where you add both channels. But the more measured statement that they make in their paper, which is never really quoted in the historical origins of string theory, is the following statement. So in case you want to read about this, either you look at their original paper or in this Birth of String Theory book, you look at the article written by Nambu, who actually quotes the correct equation. The statement that they make is more measured. They actually say that in order to explain the experimental data, they have to sum over resonances. So this you can think of as the S channel poles plus the reggae poles, which can be thought of as the T channel poles. But data seem to suggest that they had to do some kind of a subtraction, because if you did literally this, then the answer that you would get would be too big to explain the observation. So they said that you have to subtract off the oscillations that you see in the resonances. So this is some phenomenological statement. Don't take this too seriously. They were just putting it out there that maybe this is the correct way of thinking about this amplitude. And the reason why they place the second form is because this is precisely what you get from quantum field theory, or this is the picture that you have from quantum field theory, that you need to add the poles in both S and T channels. And people were indeed considering this as a model at that point of time. It went by the name of the interference model. Which one? Sorry. This is the number of the resonances, whatever peaks you see in the S channel. Same. So because of crossing symmetry, you'll have the same poles in both S and T variables. Oh, here, it's a similar index. So if you see an amplitude, you're going to see some peaks. And so you're going to sum over all the peaks. Yeah. The Regge sum would be thought of as the sum over the Regge poles. So there is something called Regge poles, which explains high energy asymptotics. And so there could be multiple Regge poles, and that are actually related to the T channel poles. Who asked that question? Yeah. Does this answer it? Okay. So motivated by this, now comes the beginning part of the development of string theory. This was number 4. There is this famous, the original pre-string paper. Anybody happens to know what ARVV stands for? Okay, I'll tell you. This is Adamolo, Rubinstein, Virasoro, and Veneziano. So in this particular case, they were looking at pion nucleon, but pion nucleon setting up the scattering amplitude problem is quite a hard problem. So what ARVV did was a toy version of this problem. They were looking at pion going to pion and a vector meson, which is called the omega meson. So they were looking at a sort of a less complicated version of the original version of the problem. This was easier to analyze. And they were looking at the Dolan-Horn-Schmidt way of doing things, which was in terms of the sum rules that they had postulated. And they found the following, that if you take the absorptive part means that the amplitude has a discontinuity. So typically the discontinuities could be because of poles. So suppose you have, let's say, as an example, amplitude 1 over s minus 1 plus 1 over t minus 1. There are poles in this amplitude at s equal to 1 and t equal to 1. So when you calculate the imaginary part, the way that you define the imaginary part is by taking s plus I epsilon, keeping t fixed. So this is the imaginary part in the s variable, minus s minus I epsilon, keeping t fixed, and dividing by 2i. So in this particular case, you would actually get something that is proportional to a delta function. So if you do things correctly, you are going to get minus pi times delta of s minus 1. Okay. So what they found is that the imaginary part of the amplitude should take on this form. And I'll explain what beta and all these quantities are, times this is in the high energy limit, so there are going to be 1 over s corrections. So beta of t is approximately a constant. Alpha of t is precisely the Regge trajectory. So alpha of t is alpha 0 plus alpha prime t. And they found that the sum rules, so the DHS sum rules they found are obeyed very well. So this was in the ARVV stuff. And now comes the Veneziano amplitude, which started off string theory. So the question that Veneziano set off to answer, so this is time frame is 67, 68. almost soon after the DHS paper came out, and the Veneziano paper came out in 1968. So the questions that he tried to answer are, instead of asking what is the imaginary part, he asked what is the full amplitude. And what are the constraints that this full amplitude should satisfy? It should satisfy crossing symmetry. And this is the statement that M of st should be equal to M of ts. And also should satisfy DHS conjecture 1 or conjecture A, that it should be expandable either in terms of the S-channel pose or in terms of the T-channel pose. So the mathematical problem that he set out to address is that he was looking for an amplitude which had this property, what is the function whose imaginary part gives that, satisfies crossing symmetry. So it should be a function that is symmetric in the two variables S and T, and also satisfies this property that it should be expandable in terms of the S-channel pole or the T-channel poles. So the first part is to ask what is the S dependence of this function whose discontinuity could take this form. And the answer is, so that part is easy to guess. So question 1, what is the function whose discontinuity in the S variable, so this is in the S variable, is of this form? So this is a Math Methods 101 question. So you want to have a function whose discontinuity is this. Now, obviously, for fractional values of alpha t, what kind of a function would you need to put in here whose discontinuity would be this? Any guesses? Okay, let me give you the answer. So the first part, so this is imaginary part of what is proportional to alpha prime s to the power alpha t minus 1. And the answer is that it should be equal to, at this stage, it should be proportional to beta t. And I'll write this minus alpha prime s alpha t minus 1. So I should have said that the discontinuity is for positive s only, because so this discontinuity is for positive s only. So if you have a function that is proportional to this, you are going to get that discontinuity. And on top of that, you're going to get some sine function. So sine pi alpha t. Okay. And then if you use the reflection identity on the gamma function, this gamma function is going to get converted to gamma of 1 minus alpha t. So that will do the job. The next step is to impose crossing. So now this function is not crossing symmetric because it's not invariant under t going to s. So since this is a constant, let's forget about the t dependence here. So now we are looking for an object that is going to have the same t dependence. So crossing implies that M of st should be proportional to beta gamma of 1 minus alpha t gamma of 1 minus alpha s. And but if it is proportional to this, I have to do something so as to recover this behavior in the largest limit. So I should have, so this is only in the largest limit. Largest fixed t. And there is a famous function called the Euler beta function, which has these properties. So this function is nothing but the Euler beta function. So beta of alpha t 1 minus alpha t, or 1 minus alpha s, 1 minus alpha t. So B is the Euler beta function. So Euler was examining this function from an integral point of view in 1730s. So this function actually has all the requisite properties. So if you worked out the discontinuity, the high energy limit, by the high energy limit at this stage, I literally mean S becoming very large. I'll talk about various limits in a bit, but at this point, S becomes very large for a fixed t. That is what I mean by a high energy limit. It'll have all the requisite properties. So this was the Veneziano amplitude. And this became famous almost overnight, literally. So the beta function actually has a well-known representation, which I'll write it down here. It will be very useful when I do the 5-particle amplitude. So the beta function has an integral representation. Now, the thing that I have not explained as yet is how does it satisfy this fact that you can expand in terms of either the S-channel poles or in terms of the T-channel poles. So now, to do that, I'll point out an observation, and then we are going to make this rigorous when we do dispersion relations, that what you can do is you can take this and you can binomially expand in powers of z. So if you, so for example, this is going to give rise to z to the power x minus 1, and then you're going to get some positive powers from here due to some binomial expansion. And then you can expand, integrate term by term. So you're doing something not completely legitimate, but if you do the integration by term, you're going to get a pole at 1 over x minus 1 plus m. So this is going to give rise to a term that is proportional to that. And so basically, because we have expanded around z equal to 0, we are going to see poles only in the x variable, but not in the y variable. Okay? Did that make sense, or was it too quick? Okay. So this was a trick. If you open Gratstein and Rijik, how many of you know what Gratstein and Rijik is? Very good. Only 2 people. So Gratstein and Rijik is a weightlifting book. It's this thick. And you, when we were graduate students, we used to open that up, look at various formulas. Now you have online resources, Mathematica, and you can actually expand various functions in terms of poles. But if you open Gratstein and Rijik or look at your famous any favorite reference, you're going to see a series expansion of the Euler beta function in terms of either the poles in this variable or the poles in this variable. So now all of you know that a gamma function has simple poles whenever the argument is a negative integer. So it is guaranteed to have poles in X and poles in Y. Now, the curious feature of this amplitude is that it never has simultaneous poles in both variables. Because imagine that this was -1 and this was -2. The denominator would be gamma of -3. And so that would kill one of the poles. Okay. Now, this would seem like some mathematical trickery. How do you know that this is actually a consistent amplitude? So now comes the remarkable fact that there was a furious development over the next year or so, and this is amazing to realize how fast people worked at a time when there was no internet and no Mathematica. They were able to do things by hand and probably do it faster than what we do nowadays. Yes?
Expanding Z is much less involved. Why can we then
yeah, so as I said, that it's a shady step. So it's basically you are supposed to think of that step as an analytic continuation. I'm going to make it rigorous by using a dispersion relation in the next lecture. Okay, so next there was a furious set of developments. This is 7. So once you have the 2 to 2 scattering, this is not good enough. This is just, you can think of this as just a tree-level approximation. How do you know it is unitary? How do you know it satisfies other kinds of consistency conditions? How do you know that you can make loops out of these amplitudes? And so that remarkable development happened almost immediately. So so this happened almost in the same year. So first, there was the 5-particle generalization. I'm going to talk about the 5-particle generalization in a few minutes. Yeah. So 5-particle generalization, and this was done by several groups at the same time, Bardakci and Rueg. Then there was Gobel and Sakita. Then Virasoro, and also by Chan and So. So this Chan is the same as the Chan-Payton factor of open string fame. And in fact, when I do the 5 particles, many of you are familiar with the U variables. How many of you are familiar with the U variables that Nima talks about in his papers? Yeah, so these U variables were introduced by Chan. And they are sometimes called the Chan variables. Then the n-particle generalization almost happened very, very quickly. And this, of course, is the famous Koba-Nielsen amplitude. Unfortunately, I haven't made a note of the day of the year, but I think it's roughly around the same time. So it's quite remarkable that all these fascinating developments happened very quickly. And starting from just a simple function like this, and I'll explain what questions they were trying to ask in order to get this 5-particle generalization. Once they had the 5-particle generalization, the rest was relatively quick. So once you have this n-particle generalization, they could actually verify something called factorization. So this is the statement that on the poles, the n-particle amplitude factorizes correctly. So suppose you have an amplitude like this, then this factorizes by becoming a product of 2 lower point amplitudes, or sum of products of lower point amplitudes. That's the statement of factorization. And that they were able to verify with the n-particle generalization. So once you got factorization, so factorization was verified by Virasoro, Veneziano and collaborators. and also by Mandelstam and collaborators. So Mandelstam and Bardacci. So they were able to verify factorization, and after they verified factorization, they found a remarkable finding that string theory, the degeneracy has what is called a Hagedorn behavior, and that's a peculiarity of string theory. So factorization implied. So this is n-particle factorization, that string theory had a Hagedorn growth. So this simply means that at each mass level, there were a huge number of particles. At each n, so at each s equal to n, so there are poles at s equal to n in the original formulas, or alpha of s equal to n. There was a huge degeneracy in states. So this was the first time that the Hardy-Ramanujan formula was actually found an application in string theory. And this huge degeneracy was also in turn responsible for the exponentially soft behavior high energy behavior. So let me just now specify what I mean by high energy behavior, because there are different kinds of high energy behaviors, and in order to clarify what I mean by this, so there are two famous high energy behaviors. One is called the Regge limit. So you have a 2 to 2 scattering amplitude. This can be generalized to n variables as well, but imagine you have a 2 to 2 scattering amplitude. It's a function of two variables, s and t. The Regge limit is when you send s goes to infinity. So the real part of s goes to infinity with t fixed. This is also sometimes called the forward limit. So if you want a physical picture, let me just draw it here. So you have two particles coming in, two particles going out, 1, 2, 3, 4. So there is, in the center of mass frame, if you redo the picture, you'd have 1, 2, and 2 making some angle with 3, and 4 coming out like that. So there is a formula. So if you are scattering massless particles, then this angle that 2 makes with 3 can be given in terms of t and s. So through that equation, 1 plus 2t by s. So if you see that if you hold t fixed and s goes to infinity, then cos theta goes to 1, and that would mean that the angle actually becomes 0, and so that's called the forward limit. And the second one is called the hard scattering limit. Or fixed angle scattering. And that's also easy to understand. Fixed angle means that you want to keep theta fixed while, excuse me. Any questions? So fixed angle means that you send s to infinity, but you want to keep the angle fixed. So that means that you have to send t to infinity as well. And in order to be considering physical angles, you have to consider negative t, because imagine that you send s to plus infinity and you also try to send t to plus infinity, then cos theta would become plus infinity. So that would be an unphysical limit. That's also something that you can consider. But if you want to consider physical angles, then you have to send s to plus infinity and t to minus infinity. So this is the physical fixed angle limit. You can also talk about unphysical fixed angle limits where your cos theta is allowed to be bigger than 1, such that s by t is fixed. Now, the behavior of the string amplitudes, the Veneziano amplitude in particular, is the following. So the Regel limit we have already done. So Regel limit, it goes like s to the power alpha prime, s to the power alpha as a function of t. And the fixed angle limit is unusual because this is not something that you encounter in physical scattering. In actual observed processes, the fixed angle is exponentially soft, which what that means is that it goes like an exponential of minus alpha prime. So alpha t can be expanded as alpha 0 plus alpha prime t. So that is that alpha prime s log s plus t log t. And depending, so the one that we have been talking about is just crossing symmetric and s and t. But you could make it fully crossing symmetric, and I'll mention that later on. But then in that particular case, there'll be an extra term here. But for now, let's not worry about it. So the exponentially soft behavior was tied in with this Hagedorn growth, and this is something that is not observed experimentally. Okay. Now, of course, as the theory progressed and people started doing more consistency checks, what happened? Now I'm going to do time travel very fast. So what happened? Consistency checks. Very soon, people realized that, at least in the original version, there was a tachyon in the theory. The theory was only consistent in d equal to 26, so otherwise you got problems with unitarity. And once you fix these problems, your intercept, which you wanted it to be half, turned out to be 1. So this was again in contradiction with experiments amongst these other problems. So there was a phase for almost a decade or so where people tried to play around with the Veneziano amplitude, put in this parameter and that parameter, try to make it consistent with phenomenology without worrying too much about consistency. And that game gave rise to what is called the Lovelace-Shapiro amplitude. So phenomenological games. So that was one logical step that people took. Lovelace was the first person to realize that d equal to 26 was the critical dimension for consistency. Shapiro also plays a very famous role because whatever I've done so far is the Veneziano amplitude. There is a counterpart to the Veneziano, which is called the Virasoro-Shapiro amplitude, which is a closed string analog of whatever I've been discussing there. In fact, the worldsheet picture hasn't entered my story at all. In fact, that was something that happened later on. The problem with the Lovelace-Shapiro amplitude was that to date, there is no n-particle generalization. So because of the lack of n-particle generalization, you cannot carry out any of these consistency checks that I've listed out here. And so this also failed as a potentially useful direction. The other logical way that people developed was tied in with the worldsheet. So the fact that there was an underlying quantum field theory, a two-dimensional quantum field theory of harmonic oscillators. So there is an auxiliary 2D QFT with harmonic oscillators. This was discovered by Nambu, Nielsen. So I should separately Nielsen and Susskind almost around the same time. They proposed that there was an underlying quantum field theory, a two-dimensional quantum field theory of harmonic oscillators that gave rise to this amplitude. And actually, there was a lot of mileage to be gained from here because whatever I've described so far is the bosonic string. So they added supersymmetry of fermions, and they managed to make things consistent. And that gave rise to a superstring. And soon, through the work of Shirk and Schwartz, people realized that the massless spin 2 particle that was there in the spectrum of this particular theory was nothing but the graviton. So it got reinvented as a potentially consistent quantum theory of gravity. So originally, the target was to explain this hadronic physics, hadron scattering, a perfectly phenomenological question to ask. Then people were driven by consistency, and the original motivation never was realized ever. And in fact, it has not been realized to date. So we don't have a consistent string picture of understanding the original question that people started addressing. Okay. So in the last few minutes of this first lecture, I'm going to talk about the potential logical inconsistency in this way of thinking. So the first obvious question is, if you look at the Veneziana amplitude, it has gamma functions. Gamma functions have an infinite number of poles, which essentially means that you're forced to think about a theory which has got an infinite number of resonances. Now, if you go back and see or if you go to PDG and look at the same plot, J versus M squared, you will realize that the number of particles that they ever show on the plot stops at spin 6. Okay, so there is no experimental evidence that there are these infinite number of mesons that are lying on this trajectory. And the reason is that these guys are never really close to the real axis. By real axis, I mean that they are poles on the real axis. They actually have a finite lifetime. And the lifetime of these resonances becomes smaller and smaller as you grow higher in mass. So they are pushed off the real axis far into the complex plane. So this is roughly, it stops at spin 6, so we don't really have any data there. So experimentally, we never see beyond roughly 6 resonances, so spin 6. So here you could try to think about, okay, then why don't we actually devise a model where we can truncate. And here again, you're led to a potential problem because this amplitude, the Veneziano amplitude, I said, write it out for you. For simplicity, I'm considering just the beta function. It usually has a slope and an intercept, which I've set to convenient values so that we can think in terms of the simple function. So I said that there is a formula. I'll write out that formula for you. It takes on this form, n runs from 0 to infinity. So this is the S-channel expansion of this formula. This symbol here is what is called a Pochhammer symbol. So let me just erase that and write it out here. This is called a Pochhammer. It is defined for any n by a ratio of gamma functions. But if n is an integer, then this has a convenient expansion. It is a into a plus 1 into a plus 2 dot 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 up till a plus n minus 1. So it's a degree n polynomial in A. Now, what do you think is the problem with this amplitude? What will happen if we try to truncate? So obviously this is supposed to have poles in both variables. So you're also supposed to have poles in T. But if I truncated, I'd never be able to see the poles in T, because if I truncated, I will only ever see a polynomial in T. Okay? So if I truncate with this as the series representation, then this is not possible. So this is questionable. So that's problem number 1. Problem number 2 is that imagine that I knew that I'm supposed to recover the Veneziana amplitude in some limit. So we can actually, what we can do is we can set up kind of a bootstrap question where we ask for an amplitude with certain properties. And so you're going to get a space of theories. So typically when we set up any bootstrap problems, we're going to get space of allowed theories. I'll talk about the bootstrap more in my final lecture, but here, roughly speaking, what we mean by that is we're going to set up a consistent set of algebraic equations whose solution is going to give me a space of allowed theories. And we can ask that one of the theories, because we know that it has nice properties, should be the original string theory. So we can ask if we can recover that. So in order to set this up, we need to have a basis that allows for level truncation. Finally, imagine that you manage to solve this problem and you manage to get some interesting amplitude by solving this bootstrap question. That would still not be enough, because this is still a 2 to 2 scattering. You would need to find a way to generalize to n particles. There is a tangential comment that I should also make here, that string perturbation theory is guaranteed to break down beyond a certain energy scale. And that happens when the center of mass energy is bigger than 1 over g string square, square root of alpha prime. And the reason why you get that kind of a consistency condition is because you have to account for black hole production as intermediate states. And this is something that string perturbation theory cannot do. So this consistency condition comes because of black hole production. So to set up the bootstrap problem in some efficient way, you really have to allow for a basis that allows for level truncation. Okay? Any questions? I have 6 minutes, and I think I should be able to cover the 5-particle Veneziana amplitude in those 6 minutes. Okay. So before we discuss what a way would be to set up this basis, let's quickly discuss how the 5-particle Veneziano amplitude was derived. So this was 9, 10. So the starting point is to draw a figure for the original Veneziano. So this is 1, 2, 3, 4. And the Mandelstam invariant that comes associated with particles 1 and 2 for shorthand and convenient notation that enables me to generalize later on, I'm going to write as alpha 1, 2. And similarly, I'm going to write this as alpha 2, 3. And the beta function can be written as some integral measure. Again, I'm introducing variables that will enable me to easily generalize to the 5-particle case, U12, U23. So basically, with each alpha 1, 2, I'm going to associate a U12, an auxiliary variable, and with this one, I'm going to associate U23, subject to the condition that U23 is equal to 1 minus U12. And the reason why you have this condition is because you don't want simultaneous poles in the variables alpha 1, 2 and alpha 2, 3. So imagine that the integral measure, so imagine that this was an integration of a du12 and u23 was related in some way such that it did not go to 1 when u12 went to 0, then that would actually correspond to a potential extra poles in the variable u23 as well. So imagine that u23 went to 0 when u12 went to 0 as well. So that would mean that it'll have poles in both these variables, alpha 1, 2 and alpha 2, 3. Okay. So to avoid simultaneous poles, in alpha 1, 2 and alpha 2, 3. Yeah, sorry. Yeah, thanks. This condition here that I've written for the u variables are also called the duality constraints in the old literature. So whenever you see the word duality, this referred to what in modern language can be called worldsheet duality. So this is not the current way that we use duality in modern string theory, which has S duality, T duality, and all that. So this is the worldsheet duality. So the generalization in the 5-particle case is actually now straightforward. So you have 5 particles, 1, 2, 3, 4, and 5. So the amplitude here, we are going to write this as integral some measure, and I'm going to specify what that measure factor here is. Now you write down with your eyes closed. So every time you see adjacent variables, you introduce u12, u23, u34, u45, and u51, and raise it to the corresponding alpha power. Second step is to identify what do you mean by the duality constraints here. So we don't want simultaneous poles in U1, 2. And now, what are the dual variables in this particular case? So in order to understand what the dual variables in this particular case are, let's consider an example. So suppose you are considering phi cube theory as an example. Let's say colored scalars. So you will realize that you can never have something that looks like 1 by alpha 1, 2 divided by 1 by alpha, say 5, 1, or alpha 1, 2 and alpha 2, 3. So this is not allowed. So because you're injecting momenta here, so you can never, so these alphas cannot share a common index when you are when you're writing down the corresponding possibilities for the poles. So the condition that you have is that when U1, 2 goes to 0, so let's write down the condition. So duality constraints. When U1, 2 goes to 0, this implies that U2, 3 and U5, 1 should go to 1. And so this implies that U1, 2 should be equal to 1 minus U2, 3, U5, 1. Similarly, now you can write down all the rest of the duality constraints with your eyes closed. So now what happens when U2, 3 goes to 0? So what is going to be the duality constraint? It's going to be 1 minus U1, 2, U3, 4. U3, 4 is given by 1 minus U2, 3, U4, 5. U4, 5 is 1 minus U3, 4, U5, 1. And finally, U5, 1 is 1 minus U1, 2, U4, 5. So you have in all 1, 2, 3, 4, 5. So 5 duality conditions. 5. So if you do the counting, 1, 2, 3, 4, 5 variables. And so obviously these cannot be all independent, otherwise everything will get fixed and you have nothing to integrate over. So after the break, I will write down the solutions to these duality conditions and present to you the final form of the 5-particle amplitude. So I'll stop there for now.
Please ask questions.
About this generalization you did, I have to imagine, okay, if I close my eyes, then I would have said that in the 4-particle case, I would have had 4 U variables rather than 2. So I guess that this is related to the solution that will happen here.
It's an excellent question, but if you repeat this logic for this case,
I guess 2 of them will be set to 0.
By the 2 of them will work out to be same. So you can actually write down a similar condition, exactly what you're saying. So you would actually introduce U1, 2, U2, 3, U3, 4, and U4, 1. And you write down exactly the same things. So U1, 2 is 1 minus U2, 3, U4, 1. Then U2, 3 is 1 minus U1, 2, U3, 4. And then you have U3, 4 is 1 minus U2, 3, U4, 1. But now you see U3, 4 is the same thing as U1, 2. Right? And so U4, 1 is 1 minus U3, 4, U1, 2. And you can see that this is the same thing as that. So you don't have the, so immediately you see that 2 variables are related. And then when you actually solve for that, you will see that you can eliminate one of the variables.
Okay. And integration measure is also...
Integration measure I will talk about. So integration measure actually has to be invariant under cyclic symmetry. That's a little subtle. I'll talk about that after the break.
Okay. Okay.
Because this is before you introduced any, before you realize that there is an underlying SL2R symmetry. So this is before conformal invariance and all that.
Any other question? If not, let's thank speaker again. And then we will meet again in 10 minutes, 4:45.